In last session, we tried to look into the matrix representation of Jacobi or Gauss-Seidel method, or any basic iterative solver method. We classified Jacobi and Gauss-Seidel as basic iterative solvers, and from the matrix representation we also found out the iteration matrix G, and observed that for a certain property of G, that is matrix norm of G must be less than 1. If we start with any guess value, the iteration should converge to the exact solution of A x is equal to B. And that is because the error between the guess value and the actual solution, which is maybe at kth iteration level, this is x k minus x star being the actual solution. This error will reduce in the next iteration level as it is multiplied by the iteration matrix G. So, if this multiplication reduces the length of the error vector, then after number of iterations the reductions will be multiplied on each other and it will go to an infinite small value, and therefore, this should converge to the exact solution. Now, there is another issue which we are discussing, that when the iterations converge to the exact solution, we can see that there is practically no difference between the guess and updated value, they also converge. So, we will also look in the convergence from the perspective that the guess and updated value are being practically same, they are also converging, and what are the requirements for them. So, we start with assume that convergence is achieved at k plus 1th step. The convergence step then is x k plus 1 is equal to g x k plus f. Now, the step before that, which is kth iteration step, here it is not converge. Convergence means the difference from the exact solution and the actual solution is of the of a very small number, and we make a criteria for that. Say this number is 10 to the power minus 8. When the difference is less than 10 to the power minus 8, we will tell that it has converged. So, let us assume that this convergence has been done in kth iteration, k plus 1th iteration step, and in kth iteration step, though it is not converged, but the relation of the guess and updated value is similar, x k is equal to g x k minus 1 plus f. So on, we can come down to first iteration step, which is x 1 is equal to g x 0 minus f. Using the above relationships, we can write x k minus 1 is equal to g of x k plus 1 minus k is equal to g of x k minus 1. Using these two, we can write this x k plus 1 is equal to g of this. Now, again using the next one x k, we can write that x k minus 1 is equal to g of x k minus 2 g of x k minus 2 plus f. So, if we subtract from these two, we will get x k minus x k minus 1. So, this minus this minus this is minus x k minus 1 is equal to g of x k minus 1 minus x k minus 2. So, if now this we substitute by g of x k minus x k minus 2, we will get g square x k minus x k minus 2, and so on we will get g to the power k x 1 minus x 0 till we come to this equation. So, the difference is also being multiplied by g to the power k, difference from the guess and updated value. So, we write x k plus 1 is equal to minus x k is, so on it is g to the power k x 1 minus x 0, and the first iteration step is x 1 is equal to g x 0 minus f. So, substituting x 1, so what we will do, we will substitute x 1 into the relationship A. We can write that this combination g x k minus 1 x k etcetera g to the power k I minus g x 0 plus f. Now, I minus G is the initial requirement was that I minus G must be a non-singular matrix. So, if it is a non-singular matrix for any x 0, it is multiplied by G to the power k, this should be a very small number if G also again has a matrix norm less than 1. So, we can say that for convergence x k plus 1 and x k will have practically same value, and therefore, the difference is infinite small, which will need that x k plus 1 minus x k is less than epsilon. We got x k plus 1 is minus x k is g to the power k I minus g x 0 plus f. X 0 can be assume that I minus g is a non-singular matrix, which is requirement for a Gauss-Seidel step. X 0 is an arbitrarily chosen vector. So, x 0 can be anything. Whatever be the value of x 0, this value has to be less than a very small number epsilon. This value has to be less than value has to be an infinite small value, and that needs that the convergence of k plus 1th step, which is x k plus 1 minus x k will be same convergence in that term will happen only if the norm matrix norm of g k plus 1 goes to 0. Then this value if g k plus 1 is, if this happens, then this value should also go to 0 or should be less than epsilon, and this is again possible if matrix norm of G is less than 1. So, we can look into two steps things. One is that if modulus of if matrix norm of G is less than 1, then the solutions will converge in a sense that the difference between two guess and updated will be is essentially 0, a very small number. The solution the iterations will converge to a value, and the converged value will be the exact solution. So, both things are satisfied if matrix norm of G is less than 1. So, A x is equal to B will look into convergence and accuracy of the iterative method. A x is equal to B, we have the iterative step x k plus 1 is equal to g x k plus f. If matrix norm of G is less than 1, then if matrix norm of this is not g k plus 1, if matrix norm of the if G is less than 1, matrix norm of G to the power k plus 1 is basically multiplying the matrix several times, this goes to 0. And once this happens, the iterations converge for some k for which the difference between guess and updated value is very small. Also, the converged solution x k becomes practically same as the exact solution x star, because these two differences are small. So, therefore, if the first thing happens, this will happen for this particular criteria, and for which this should also happen, or if the reverse happens, like the solution practically converges to the exact solution, we will see that the iteration guess and updated value has also converged to the same value. So, if the iterations at all converge, if we come into a stage that the x value is not being updated, guess and iterations are being same, then the iterations have converged to the right solution, and that is the robustness of this particular technique, Gauss-Seidel or Jacobi, or we will see successive over relaxation as a class of these methods. This class of technique, that if we can have a converging solution, converging iteration, the final result must be same as the actual result. So, we can sum it up as if the iterations converge, they will converge to the exact solution. Now, the questions come that under which case iterations will converge. Of course, we know that by now that mod G or matrix norm of G should be less than 1, and when matrix norm of G will be less than 1, we have to look into the matrix, because we are doing very two steps to get G matrix. From we are doing one type of splitting of A in Gauss Jacobi, and we are doing another type of splitting of A in Gauss Seidel, but this is basically splitting of the matrix A. So, through splitting of the matrix A, we are getting the iteration matrix G. The iteration matrix G has a norm less than 1. This is our requirement for convergence of Gauss Seidel or Jacobi methods, and this requirement is satisfied based on what? Based on how is the A matrix. So, you have to look into the A matrix and see that in under which cases splitting of A matrix gives us a G which has matrix norm less than 1. Another thing we can also see that the value x k plus 1, if we go to the maybe we can go to the previous slide, and or here we can see also that this value x k plus 1 minus x k is something is this is like this value x k plus 1 minus x k is g to the power k into something. Similarly, x star minus x k is also g to the power k into something. So, all this is some initial value multiplied with g to the power k. So, what is g? If g is a very small number, within very less number of steps g to the power k will be a infinite small number. If g has to be less than 1, but if g is close to 1, say for example, g is 0.9, then it will take large number of steps. Consider to the case g is 0.1 or matrix norm of g is 0.1, it will take less number of steps. So, how fast will be the convergence, that will also depend on how is the G matrix, and how is the G matrix, that depends on how is the A matrix, because G is coming through splitting of A. So, we will look into the properties of A matrix for which these things will hold. A matrix A is called weakly diagonally dominant matrix. We will look into few definition and the definitions of diagonally dominant matrices. A weakly diagonally dominant matrix, if the any diagonal term, we consider any diagonal term that is greater than the all off diagonal terms of that particular sum of all off diagonal terms of that particular row in their absolute form, greater than equal to, then we call weakly diagonal. They may be greater than the sum of off diagonals or maybe is equal to the sum of off diagonals. We call it strictly diagonally dominant if all the diagonal terms is greater than equal to sum of the off diagonal terms of that particular row, except the diagonal term of all diagonal terms. We call it to be irreducibly diagonally dominant if for all j it is weakly diagonally dominant, but there is at least one row at least one j for which the diagonal dominance is there. So, for all j absolute value of the diagonal term is greater than equal to sum of the absolute value of the off diagonal terms, but there is at least one j for which at least one row for which the diagonal term is absolute value of diagonal term is greater than, this is not greater than equal to, this should be greater than the sum of diagonal terms. So, and the requirement is that another thing is that irreducibly or strictly diagonally dominant matrices show non-zero pivots, at least in a permuted form, and hence are non-singular, not in permuted form, also in non-permuted form also strictly diagonal matrix or irreducibly matrices show non-zero pivots. So, the permuted form is not important here, and therefore, these matrices strictly diagonally dominant or irreducibly diagonal dominant matrices are non-singular also. Why are we discussing this? Because it has a relation. Remember at the beginning when I was introducing Gauss Seidel or I was introducing Jacobi, I said that this is only valid for diagonally dominant matrices. Now, we will see that only for diagonally dominance or irreducibly diagonally dominant matrix, the G will be such that the matrix norm of G is less than 1, and that is why these methods will be valid. If A is strictly diagonally dominant or irreducibly diagonally dominant matrix, then the associated Jacobi or Gauss Seidel iterations converge for any x 0. This is the theorem for convergence of any iteration. When the Jacobi or Gauss Seidel iterations converge, when G has a matrix norm less than 1. What is G? G is G is a split, comes from splitting of A, and this condition if we look into A comes as if A is strictly diagonally dominant or an irreducibly diagonally dominant matrix, then associated Jacobi or Gauss will converge. That means, G will have matrix norm less than 1. So, for which type of matrices this will converge? For example, the first matrix 5 0 4 1 3 2 2 6 8 is A matrix, right. So, these are the A matrices. Now, if I look here, this is a diagonally dominant line, 5 is greater than sum of this. This is a weakly diagonally dominant, 1 plus 2 is equal to 3, 2 plus 8 is equal to C. However, this becomes an irreducibly diagonal dominance is here, irreducibly diagonally dominant matrix, and this is a diagonally dominant matrix. So, for these two, this X is equal to B can be solvable using Jacobi or Gauss Seidel. If in case this would have been 4, in case instead of 5 this is 4, we could not have been able to solve this equation, because then it would have been a weakly diagonally dominant. So, for weakly diagonally dominant matrix, Gauss Seidel or Jacobi cannot work. You can try, we will discuss about writing our own program, but you can try also this by hand. You can paper pencil, you can try few steps and see what is happening to this. You will see that the values are not converging, x k plus 1 minus x k, if it is weakly diagonally dominant, x k plus 1 minus x k is not reducing, it is increasing or remaining constant at a high value. If it is not a diagonally dominant matrix, like if we look into the first row, 2 plus 4 is equal to 6, which is 5 plus 4 is equal to 9, which is greater than 2, then it cannot be solved. Also, if we think of doing a row permutation of this matrix, like I will permute these rows, I will again permute this and this. If we think of a row permuted form of this matrix, it does not remain a diagonally dominant matrix. However, the solutions will remain same, because row permuted form and the actual form should give us same solution. But if we do row permutation, the matrix loses diagonal dominance and we cannot solve it using Jacobi or Gauss Seidel. Though row permutations remain the solution same, solutions exist and solutions are same with a diagonally dominant matrix or irreducibly diagonally dominant matrix and the row permutated matrix form of that matrix, solutions are same. However, the row permutated form, as it does not remain diagonally dominant, cannot be solved using Jacobi or Gauss Seidel method. Why? Because of the fact that G has been changed. So, in case we get a matrix which is solvable, but is not in a diagonal dominant form, we can try row permutations and give it to a diagonal dominance form, and only in the diagonal dominant form the matrix can be solved. This cannot be solved using a Jacobi or Gauss Seidel method, because this is, though these two matrices are permutated form of each other. However, 2 plus 3 is equal to 5, which is greater than 1. So, this is not a diagonally dominant form. So, it cannot be solved using this. Here comes another important definition, is that the maximum modulus of eigenvalues of A is called spectral radius of A or rho A, and this is given as any, for any matrix norm. We can take 1, 2, 3 up to P or infinite matrix norm. Matrix norm of matrix A to the power k to the power 1 by k, and as limit k goes to infinity. This is rho of A. So, maximum, and this is same as the maximum modulus of eigenvalues of A, spectral radius. So, any matrix raised to a high power, and then we take matrix norm and then take say that root of that matrix to the power it was raised. The limit is the spectral radius or the largest eigenvalue of A. This is the definition. So, let A is equal to m minus n, m n pair is called regular splitting if m is non singular, and M inverse and n are non-negative. Then A is equal to M n is called a regular splitting of matrix A. A non-negative matrix means all elements of that matrix are non-negative. Let M and n be a regular splitting of matrix A, then rho M inverse n is less than 1 if A is non-singular and A inverse is non-negative. So, if M and n are regular splitting of A, then rho inverse n is rho of M inverse n less than 1 is non-singular if A is non-singular and A inverse is non-negative, and the iteration step, in that case the iteration step x k plus 1 is equal to M inverse n x k plus M inverse b will converge to rho of converge if this rho M inverse n, or this is basically the G matrix, right. This is basically the G matrix. This will converge if the matrix norm of G to the power k is very small, or matrix norm of G is less than 1, which is spectral radius of G is less than 1. So, if spectral radius of G is less than 1, x k plus 1 G x k plus f will converge, and this will happen if M and n are regular splitting of matrix A. That means, M is non-singular and M inverse and n are non-negative. And now, there was a scientist named Greshkorin who found out a theorem on the diagonal dominance of a matrix and its eigenvalues, and as a corollary of the theorem we can say that this regular splitting with as above conditional spectral number rho M inverse n is less than 1 can only be obtained for irreducibly or strictly diagonally dominant matrices. This comes from Greshkorin. So, if the matrix A is strictly diagonally dominant or irreducibly diagonally dominant, we can get a regular splitting of M and n following our Jacobi or Gauss-Seidel method, and then we will also see rho of M inverse n, where M inverse is and n are non-negative, rho of M inverse n is less than 1. A inverse will also be non-negative and A is non-singular in that case, if we have dominant or diagonally dominant matrix. So, rho G is less than 1 and diagonal dominance, they are actually related, and this relation comes through Greshkorin theorem. I am not going into detail of Greshkorin theorem here, but this discusses how should be the depending on the eigenvalues of the matrix, how should be the diagonally dominant diagonal term and off diagonal term and their arrangements. So, now what we got is that if the matrix is non-singular, A inverse is non-negative, if it can have a regular splitting, which is for a irreducibly diagonally dominant or strictly diagonally dominant matrix, then G should have convergence, G should have a spectral radius which is less than 1. Therefore, matrix norm of G must be less than 1 and matrix norm of G to the power k must go to 0. So, let G be a square matrix such that rho of G is less than 1, then I minus G is non-singular and iteration G x k plus 1 is equal to G x k plus 1 is equal to G x k plus f. This iteration also converges for every f and x 0, and its converse is also true. So, if G is a square matrix, so that rho of G is less than 1, obviously I minus G will be non-singular and the iterations will converge, and the converse statement is also true, and this happens if and only if A is a diagonally dominant or irreducibly diagonally dominant matrix. So, these are the cases in which we will have convergence of the iterative methods, and this is very important. Gauss-Seidel and Jacobi are very robust methods, but only for the matrices which is diagonally dominant or irreducibly diagonally dominant. Now, we can see that the convergence depends on G. Rho of G has to be less than 1. Spectral radius, we made things much simpler and much easier to quantify at this stage. Instead of looking into the matrix norm of G, we can just consider the spectral radius of G or the largest eigenvalue of G. If that is less than 1, then the equation system will converge, and that should be done for any diagonally dominant or irreducibly diagonally dominant matrix. Now, the question comes is that how fast will they converge? What will be the number of steps when we run a Gauss-Seidel or Jacobi program? How many iterations will it need? If it needs a very large number of iterations, there is not much need of running the iterative methods, because probably the direct solvers can give us faster solution, but if it takes less number of iterations, we can do it. So, how to see what is the rate of convergence, or how fast do they converge, how many steps needed for convergence of an iterative method. It is also important to see, which we will do in the later session also, that if we can improve the rate of convergence, if we can do certain things so that the convergence rate improves, or if we play with the splitting of the matrix, so that we can get faster convergence. So, we before going into this, we will try to define two more parameters regarding convergence. One is the convergence factor. Let the error at kth step be dk, which is xk minus x star is the exact solution. The difference between the guess vector and the solution vector is the error, we define it as dk. Dk is g to the power k into d0, initial error into g to the power k, we have seen that earlier. The convergence factor, which is defined by rho, is given as rho is equal to limit k goes to infinity. So, this rho is not spectral radius, rho of a matrix is the spectral radius, simple rho is the convergence factor, there are two rhos, must not be confused. Rho limit k goes to 0 dk by d0 1 by k to the power 1 by k. For faster convergence, the convergence factor must be solved, must be small. So, how should we determine convergence factor? We after kth iteration, after k is a large number iteration, we see what is the solution, what is the error, and the ratio between these two errors to the power 1 by k is the convergence factor. If the factor is small, that means it is the error is reducing in a fast way. So, convergence, so we will need less number of iteration steps for convergence factor. However, if we look into the previous slide, this definition depends on the term d0, right. We have to start with a d0 and see what is happening. So, a better definition is given, which in which we do not need to we do not have to need we do not need to depend on x0, we call it general convergence factor, and it is defined as independent of initial guess phi. General convergence factor is limit k goes to 0, maximum of x0 which belongs to r to the power n dk by d0 to the power 1 by k, and this is maximum dk is g to the power k d0, maximum of matrix norm of g to the power k, vector norm, these are ratio of vector norm g to the power k d0 by d0 1 by k. Now, by definition, this is the definition of say vector norm of any vector b is equal to maximum of x0 belongs to R, matrix norm of any matrix B is maximum of x0 belongs to R, B x0 by x0. So, this is the definition of matrix norm of g to the power k. So, we get limit k goes to infinity matrix norm of g to the power k to the power 1 by k, which is nothing but spectral radius. So, if we try to see maximum of the convergence factor, maximum value of the convergence factor for any guess x, any guess x0, we will see that is the general convergence factor, which is spectral radius. So, spectral radius, now the smaller the convergence factor, faster is the convergence. Therefore, smaller the spectral radius, faster should be the convergence. We need to have a matrix G whose largest eigenvalue is a small number, therefore, we should get fast convergence. And there is another term called convergence rate. For faster convergence, convergence rate must be high. So, it is kind of has an inverse relation with the convergence factor. If the convergence factor is small, then convergence is faster. If the convergence rate is high, convergence factor is faster, and convergence rate is defined as minus log of rho tau is equal to minus log of the logarithm of convergence factor, which is minus logarithm of equivalent to general convergence factor, or minus log of rho j. Smaller the spectral radius of G, higher is the convergence rate, and therefore, faster the convergence, higher the convergence rate. So, less number of iterations will be needed. So, we need to see that, and that will give an idea that how we can improve the convergence criteria through splitting, which one will give us faster convergence, Jacobi, Gauss Seidel, or some variant of it, for which we get smaller spectral radius of G. If the spectral radius of G is equal to 1, there is no convergence, it is killed, right. I minus G is singular, it cannot converge. If spectral radius of G is less than 1, this will converge, and as small as it will be, in spectral radius, this is the modulus of the eigenvalue. So, this cannot be negative. So, as small as it be, as it is in between 0 to 1, as small as it be, faster will be the convergence. So, in next class we will look into some matrices and look into the spectral radius of this of the G associated G matrix, and see for Jacobi and Gauss Seidel how is the convergence rate, and we will also see if we can do something with the matrix, or we can design a better matrix solver which will have less smaller spectral radius, so that the matrix the solver convergence in a faster way than Jacobi and Gauss Seidel. We will look into this in the next class. Thank you.